Hi and welcome to video 7 on this video series on Statistical Inference Unit 4 Topic 3 of the Specialist Mathematics course. And today we're going to talk about the margin of error and how you might be asked for the margin of error, but really we've been calculating it anyway. So the point to be made here, which is related to what you've already covered in math methods, is that the margin of error is that bit that's added and subtracted from the mean to make the confidence interval. So if you've got a sample mean here, and you want to guess where the population mean is, it could be here, it could be here, it could be down here, it could be right on our sample mean. We don't know really. As we increase n, our sample mean should become more confident though, and we get more confident in our sample, in our where our population mean is. The margin of error is the bit that is added on or subtracted from our sample mean to estimate where the population is. Now it's important to note here that I've done one here. This is one sample, and I've got a margin of error there of E because my sample, if I do lots of samples but the same size, my sigma will change in the sample, but my M will stay the same. So if I do another sample, I might get this result, and if I do another sample, I might get this result with a larger sigma. If I do another one, I might get a smaller sigma back on the sample mean. So we don't know, we'll get heaps of samples here, and maybe my population mean is here. And it sort of misses two of those samples. We don't know. But as we increase our samples and sample sizes, we increase our accuracy and our confidence. But the big picture here is that the margin of error is this bit that's added on or subtracted from the mean to give it our center, and the extremities of our confidence interval, so the margin of error is equal to that. It is the z-score of the confidence interval we're going for, so it's usually a 90, 95 or 99, and it's related to our sigma, which is probably going to be our S from our sample, and N, our sample size. So let's have a look at example 2. In a sample of 100 bolts, so N equals 100, the average mass of that, this is X bar, and the sample standard deviation, that's sigma, for a 95% confidence interval, that's Z. Determine the margin of error. What sample size would ensure that the error is less than 0.1? So it turns out we're not going to need this, but we are going to need everything else. So in A, the margin of error, which is E, is equal to Z of A times by sigma over the square root of N. And in this case, that's going to be a 95% confidence interval. It's 1.96 times by sigma, which is 1.6 over the square root of 100, and again our sample size is a nice square number, which is amazing. So it's 1.96 times by 0.16. Our margin of error is 0.3136. And in part B, we want our margin of error to be less than 0.1. As we increase n, our error goes down. So we just want to find that critical point where it's equal to 0.1, and then we'll round n up. So we want 0.1, it's going to be less than this, so our sample has to be bigger. We want 0.1 to be equal to ZA times by sigma over the square root of n. We don't know the square root of n, but we do know ZA, etc. So I get 0.1 equals 1.96 times by 1.6 over the square root of n, which means that we get the square root of n is equal to 1.96 times by 1.6 over 0.1, and I'll just do that calculation, and that gives me 31.36, and so n is equal to 31.36 squared, which is 983.4496 according to my calculation. Now 983 sample size would be not quite low enough in terms of our margin of error, so we're going to say n is equal to 984. So what sample size would ensure that? That 984 is the lowest possible sample size that would ensure that, and so we could actually be a bit cheeky here and just say n has to be greater than or equal to 984. So there's example 2. Let's have a quick look at example 3. The lifespan of a battery from a particular factory has a 90% confidence interval of S for a sample of 50 batteries. Lifespan measured in hours. Determine E, X bar, and sigma. So in this case, remember that our our confidence interval, so this is A, part 1, our confidence interval is a 90% confidence interval, so we already know that Z is equal to 1.64, but it's equal to X bar minus the standard error to X bar plus the standard error. And so therefore, we get X bar minus the standard error is equal to 122.7, and we get X bar plus the standard error is equal to 125.3. And so if I add those two simultaneous equations together, I get 2X bar is equal to 123, 248, which means that X bar is equal to 124, which kind of makes sense. 124 is 1.3 above that, 1.3 below that. And if X bar is 124, then X bar minus E is 122.7, that's a 5, and we get E is equal to 1.3. So there's our answer to part 2, there's our answer to part 1. So I'll make a note of that. So I may have asked them the wrong way. And then of course, because we know E, so this is part 3, E is equal to 1.3, and we know E is equal to ZA times by sigma over the square root of n, and we're being asked to find sigma. Now we also know n is 50, so we get 1.64 times by sigma over the square root of 50 is equal to 1.3, and that should say 1.3 there. And we can put that in the calculator as sigma equals 1.3 times the square root of 50 over 1.64, and we get this. .605 as our sigma score. So there's those calculations. So just keep in mind, if you know the confidence interval, then you do know a fair bit, and you can use that and use it simultaneously like I've done here to calculate all your values. Now this is a change of confidence interval type question, so determine the 99% confidence interval. Once we've done all this background work, this bit's actually pretty easy because we've got all the information we need. So Z99 is equal to 2.58, and therefore the confidence interval 99 is equal to X bar minus E, X bar plus E. X bar hasn't changed, but E has, where E is equal to 2.58 times by sigma 5.605 over the square root of 50, and so that's equal to divide that by the square root of 50, and then multiply that by 2.58, and that's equal to 2.045. And of course X bar is equal to 124, so we get our confidence interval 99 equals 124 minus 2.0, I'll say 2.05, and 124 plus 2.05, and that's equal to 121.95 to 126.05. And I'm happy with that because it is a wider interval than our original 90% interval was, and we expect that. We expect to have to increase the interval size to increase the confidence. And finally, example 4. So we have during an external exam, the initial marking team graded 20 papers and got the following results. So we have 20 exam results. Determine the 95% confidence interval for the value of the actual mean mu of the test scores. Comment on the reasonableness of your solution. So it's important to note here that n is equal to 20 and Z95 is equal to 1.96, and I'm going to go and add all these data to my calculator to work out my standard deviation and my mean now. So I'll do that, and you'll see it happening quickly on your screen. So my data here is that mu is equal to 76.55, and of course that's not mu, that's x bar, that's our sample mean from that sample, and of course I'm going to use my sigma to be approximately equal to that sample standard deviation, which is 18.09. We'll just leave it as 18.09 there, and now I can do my full calculation, and that is my confidence interval, and it's a 95% confidence interval, is equal to, and again I go into the x bar minus e, x bar plus e standard error, where e is equal to 1.96 times by 18.09 over the square root of 20, and so this is equal to 7.928 is our standard error, and I can do the calculation now. From here, x bar is 76.55 minus my answer, and that gives me a lower bound of my confidence interval of 68.62 and an upper bound of my confidence interval of 84.4748 rounded up. Now let's have a quick chat about the reasonableness of our solution. That's my 95% confidence interval for the actual mean of test scores. So I'm 95% confident that the population mean of these test scores will be between 68.6 and 84.5. But in terms of reasonableness, the first obvious thing should be that n is less than 30, and that could potentially be a problem for us. So we are taking data from a very small sample set. And secondly, because the n is so low, we actually get a really wide distribution. So it's quite reasonable, but only because we have such a wide distribution, there's a good chance that Z does exist in there. This encapsulates a lot of our data. 1, 2, 3, 4, 5, or 68, not quite. So 4 will say encapsulates a lot of our data, but not that much of our data is included within this data set. So that's problematic for us as well. But that's okay. It's the best we can do with the data we've been given. And instead of just getting that point estimate, which is to say, oh, I think the average of the population will be 76.55, we'll actually evaluate it in more depth by looking at the confidence interval and the width of the confidence interval and the size of n, which is statistically a better thing to do. So that's the end of this and this topic. There's 15F confidence intervals that you can work on now. I hope you've got a clear understanding of that, but obviously ask questions if you need to. We'll see you in the next topic. All the best.